Welcome, everyone, to this comprehensive step-by-step university-level explainer. Today, we're tackling one of the absolute most classic and honestly notorious challenges in dynamic system modeling. I'm talking about the inverted pendulum on a cart. Think of a massive rocket desperately trying to balance on its thrust vector, or, a Segway keeping a rider from face planting. We are looking at a system in a constant, literal state of physical crisis. It's fundamentally unstable. It wants to crash. So what's our mission in this explainer? We are going to mathematically tame that crisis. To do it, we're constructing a rigorous step-by-step derivation using Lagrangian mechanics, taking us all the way from foundational physics straight into a nonlinear state space simulation. Let's get into it.
Okay, so let's look at our core methodology. If you've ever tried to solve a really complex multi-body system using standard Newtonian mechanics, you know exactly how fast it turns into a messy nightmare. I mean, you've got free body diagrams everywhere, you're resolving complex vector forces, tracking internal reaction forces that, frankly, we don't even care about. The Lagrangian method, though, it gives us this incredibly elegant alternative. It's a strictly energy-based approach. So rather than mapping out all those chaotic vectors, we simply track scalar energies. Specifically, we look at the kinetic energy, which we call T, and the potential energy, which we call V. Here's our roadmap for this explainer. 1. The modeling challenge. 2. Translating geometry to energy. 3. Expanding the kinetic energy. 4. The master Lagrangian. 5. Extracting system dynamics. And finally, 6. Matrices and state space simulation.
Section 1. The modeling challenge.
Notice right off the bat how the physical reality of this system is totally split into two separate but intimately linked domains. First up, we've got the linear domain. This is the cart, it has a mass of capital M, and it operates purely back and forth along a simple one-dimensional track. Its position is just defined by the variable x. Easy enough. But then we have the angular domain. This is the pendulum itself, featuring a point mass of lowercase m sitting on the end of a massless rod of length L. It swings in an arc, and that's defined entirely by the angle theta. Now here's the kicker. The only way we can influence this entire interconnected setup is through a single input. That's the active control force F, applied linearly straight to the cart.
And this brilliantly illustrates our universal mathematical translator. To bridge those two totally distinct physical domains, the linear and the angular, we're going to use the Lagrangian engine. It's actually kind of beautiful. By simply subtracting the system's total potential energy from its total kinetic energy, we formulate the Lagrangian L. We then just feed that L into the operator equation. This one single mathematical operation is going to reveal the complex rules governing both the cart and the pendulum. And the best part? We don't have to draw a single vector arrow to do it.
Section 2. Translating geometry to energy.
But before we can even start talking about velocity or energy, we absolutely have to lock down our coordinates. Look at how we map the absolute position of the pendulum's center of mass. Because our pendulum is literally pinned to a moving cart, its position out in the real world is a combination of two things. Its absolute horizontal position anchors dynamically to our moving cart's x-coordinate, plus the horizontal trigonometric component of the rod, which is L sine theta. The vertical position is much simpler, just L cosine theta. Boom. We now have a perfect geometric snapshot of the system.
Now that we've got that absolute position, we need to apply a time derivative. This elegantly translates our static geometry into dynamic, real-world velocity. Because our coordinates contain variables that are actively changing over time, specifically x and theta, we have to bust out the chain rule. Look closely at the resulting horizontal velocity. Notice it's not just the velocity of the cart. It actually includes a totally new term derived from the angular rotation. This shows us mathematically exactly how angular rotation creates coupled linear velocity in the real world.
Section 3. Expanding the kinetic energy.
So we take those dynamic velocities we just found and we plug them straight into the standard everyday kinetic energy formula, 1/2 mass times velocity squared. That means the total kinetic energy of our system, T, is basically the sum of two parts. First, you've got the cart's pure linear energy. Second, there's the pendulum's much more complex multi-axial energy, which squares both the horizontal and vertical velocity components we just derived a second ago.
Now, before we actually expand all that math out, we need to clearly define a really specific concept we're about to run into, the coupling term. In dynamic modeling, a coupling term is essentially a nonlinear mathematical expression that captures the physical interaction, the mechanical tug of war, if you will,
between multiple moving bodies. Seriously, understanding this tug of war is the entire reason this pendulum is so notoriously difficult to keep under control.
All right, so when we expand the algebra, FOIL out those squared terms, and group the components together, we wind up with expand that algebra, out pops this specific coupling term. This mathematically represents that physical tug of war. When the cart accelerates, it physically tugs the pendulum, and when the pendulum swings, it pushes right back on the cart. This single, nonlinear term captures that entire messy relationship.
Section 4, the master Lagrangian.
Okay, so we've got our kinetic energy locked in. Now we need our potential energy, V. Since the cart just rolls along a level track, only the pendulum is actually changing height. So V is simply mass times gravity times height, which gives us mgl cosine theta. We subtract this potential energy from our expanded kinetic energy, and check it out. We achieve this beautiful synthesis. This is it. The master Lagrangian, the entire physical reality of this system, every single mass, every motion, every crazy coupling, and the relentless force of gravity is perfectly encapsulated in this one single algebraic line.
Section 5, Extracting System Dynamics. Time to crank the handle on this engine. First, we apply the Lagrangian differential operator to our linear variable x. We take the partial derivatives of our master Lagrangian and then follow that up with the time derivative. I'm not going to read out every single algebraic step here, but just look at the final result. This is the official equation of motion for the cart. Notice how the right side of the equation equals F. That tells us the linear response is actively driven by our external control force. But look over at the left side. We've got the combined mass undergoing linear acceleration, but it's modified reactively by that centrifugal force feedback pouring in from the swinging pendulum mass. Next up, we do the exact same Lagrangian operation, but this time for our angular variable theta. Again, we run through the derivatives, but look closely at the final result for this one. Because there is literally no motor attached directly to the pendulum's pivot joint, the generalized force on the right side of the equation is strictly zero. This is actually profound. Mathematically, it dictates the system's unforced natural tendency to just fall over. That gravity term there, g sine theta, it acts as this relentless disturbance, constantly pulling the pendulum away from its super precarious balanced state at 0 degrees.
Section 6, matrices and state space simulation.
Now, we've successfully derived our equations, but by grouping our variables, we can actually stack those two equations into an incredibly elegant matrix architecture. This instantly separates the system into logical, bite-sized blocks. We have the inertia mapping matrix, representing the mass and the geometry. Then our highest derivatives, so linear and angular acceleration. And finally, on the other side of the equal sign, we isolate the active forces. That includes our control input, F, and the effect of gravity constantly pulling on that pendulum. But if we want a computer to read this, to simulate this in software, we need expressions that solve directly for those highest derivatives. By mathematically inverting the inertia matrix and multiplying it across, we perfectly isolate our linear and angular accelerations. This gives us the strict state space model that is absolutely necessary for digital simulation. As you can see from the resulting math, our dynamic state is now perfectly defined by exactly 4 variables at any given microsecond in time: position, angle, linear velocity, and angular velocity.
So to visually validate all this rigorous mathematical derivation we just did, we're going to set up a computational simulation using an ODE solver. We establish a totally unforced physical scenario. The system starts completely at rest, then we give the pendulum a tiny 0.1 radian nudge, just the slightest little tip, and we make sure our control input F is completely locked at 0. Absolutely no corrective force will be applied here. Let's see exactly what our math predicts is going to happen. And here is the undeniable visual proof of our mathematical labor. Look at this state space output over just a single second. The angular tracking shows the pendulum angle. As we completely expected from that tiny nudge, it undergoes uncontrolled exponential free fall, swinging way down past 2 radians. But look at the cart's position track. Without us ever pushing the cart is actively sliding backwards in the negative x direction. Why? Well, because of the coupling term. Our math correctly predicted the reactive momentum. The falling mass is literally pushing the cart right out from under it.
And that brings us to our synthesis. We have successfully traversed this unbroken chain of truth today. We started out with raw, physical geometric coordinates. We then utilized scalar kinetic and potential energy as our absolutely flawless translators. We formulated the master Lagrangian, we extracted the equations of motion, arranged them neatly into nonlinear matrices, and successfully ran a highly predictive state space simulation. This mathematical anatomy right here
It forms the unbreakable foundation upon which all modern control theory is built.
But as much as we've accomplished, our journey here today leaves us with a bit of a cliffhanger. We've done the really hard work of deriving the exact mathematics of failure. We have mathematically proven, beyond a shadow of a doubt, that without active intervention, this system is going to crash. So the obvious imperative next question is this. Now that we actually possess the state-space matrix, how do we design the active control loop to save it? How do we calculate the precise force F required to keep that pendulum pointing straight up at the sky? Well, I'll leave you to ponder that vital step in applied control theory. Thanks for diving into the math with me today on this explainer. Keep learning and keep building.